So we have our next speaker, Professor Shiraz Minwalla from TFR.
Thank you very much. It's a great pleasure to be back at IMSC and an honor to be speaking at this conference. My talk today is titled Non-Trivially Gapped QFTs and is based on a set of papers that have been listed here in some detail. Okay, this is an outline of my talk. In this talk, I will take you through a discussion of two kinds of quantum field theories, both of which have no massless particles, and I will try to convince you that that theories that flow at low energy at low energies to topological field theories rather than empty quantum field theories have new and distinct and interesting types of properties, some of which are being uncovered in work people are doing. Okay, so let's start. Quantum field theories, as all of us know, come in two basic varieties. There are field theories that have massless particles and those that do not. Now, theories with massless particles are often complicated at long times because long times is due to low energies, and so since these theories have massless particles, they continue to interact. They can continue to interact even at very long times, and as a consequence, these theories can be complicated even at long times. For instance, in the most severely interacting theories with massless particles, single particle states don't exist because even when you go to very long times, lumps of energy keep radiating. You don't have single particle states. On the other hand, there is a sense in which theories with a mass gap, theories with no massless particles, are simpler than theories with massive particles. Okay, and that will be the focus of today's talk. And today we will only be discussing theories with no massless particles. Okay. However, theories with no massless particles may naively appear, all such theories may naively appear to be sort of the same at low energies. However, that's not true, and this is the point that condensed matter physicists have made very forcefully over the last 10 or 20 years. Theories with no massless particles come in two varieties. There are those that, at low energies, descend to a completely empty and completely trivial theory. And then there are theories which, at low energies, reduce not to a completely trivial theory, but a topological field theory. Okay? So I will call the first kind of theory trivially gapped theories. The second kind of theories I will call non-trivially gapped theories, those that at low energies reduce to topological field theories. Okay. Trivially gapped quantum field theories are very familiar. They have well understood properties. They host stable particles. These particles have either integer or half-integer spins. They're either fermions or bosons. When they weakly couple, these particles obey either Fermi or Bose statistics. They have occupation number statistics given by Bose-Fermi distribution functions. And they always have well-defined S matrices. And S matrices have well-understood structural features. For instance, they obey crossing symmetry. Okay. Non-trivially gapped quantum field theories, massive quantum field theories, are less well understood. And you may wonder whether all these properties that I've listed in this top point apply to non-trivially gapped quantum field theories. I don't think the answer to this question is known in general. In this talk, I will describe the initiation of an investigation for some of these questions in the context of a particular example. And the example we will study is Chern-Simons theories in 2 + 1 dimensions minimally coupled to massive matter fields. Okay? Much of what okay, let's move on. First, okay. So in the next 3 slides, I'm going to review what these Chern-Simons theories are. Okay? So Chern-Simons theories are gauge theories in 2 + 1 dimensions, and they're governed by an action that is listed here. The action involves the gauge field y mu in some combinations. Okay. Observables in this theory are the partition functions of the Chern-Simons theory on various manifolds, as well as partition functions in the presence of Wilson lines and various representations. Now, if you're not familiar with these theories, for those of you who are not familiar with these theories, I'm going over the slide I give you a one-page summary of their properties. The first important thing about these theories is that pure Chern-Simons theories, the equation of motion of pure Chern-Simons theories is that F mu nu is equal to 0. So the field strength in these theories vanishes. Now, all local information about a gauge field is contained in its field strength. So the fact that the field strength vanishes tells you that locally nothing happens in these theories. Okay? Anything that happens in these theories is a global effect, something associated with boundaries. Okay? So these theories are theories without local excitations. Relatedly, if you look back at the Lagrangian that defines these theories, the Lagrangian does not contain the metric of the spacetime manifold in which the theories are formulated. And so these theories are what are called topological field theories. They care about the topology of the manifold in which they're formulated, but not in the detailed metric. They have no local degrees of freedom. Now, another thing about these theories that is true is that these theories are only well-defined if kappa or k, the level of these Chern-Simons theories, is an integer. When that's not true, these theories are not gauge invariant. Okay. This is tightly related to a fact that some of you might be finding strange. You know, when we're students, we're told that we should build Lagrangians out of the field strength, because that's the way of making a Lagrangian describe gauge invariant physics. Yeah, Chern-Simons theories are defined by a Lagrangian that's built out of the gauge field itself and not out of the field strength. And yet turns out to be, yet they describe gauge invariant physics in a slightly interesting way, but that mechanism only clicks when k is an integer. Okay, and as I've already mentioned, you know, because this theory is topological, the standard observables of a quantum field theory, namely correlation functions of local operators, makes no sense. Okay, the paradigmatic observables of these theories are expectation values of tangles of Wilson lines or Wilson loops in these theories. The Wilson lines have some topology, and they're also labeled by a representation. Okay. Now, something that will be important for my talk, and this is something that's well known and has been well known for 30 years, is that these Chern-Simons theories enjoy, these pure topological Chern-Simons theories enjoy invariance under a certain duality. This duality has a name, it's called level rank duality. I'm going to review it for you. Level rank duality is the assertion that, okay, this is some technicality, you can forget about it. That the UNK theory, the UNK Chern-Simons theory, is dual to, which means it's the same thing as the UK minus N Chern-Simons theory. Okay, so the Chern-Simons theory that you get by exchanging level and rank, the two Chern-Simons theories that you get by doing that are the same theories. Now, what does the statement mean? The first thing that the statement implies is that the partition function of the two theories on the same manifold are the same. Secondly, also, this statement implies a relationship between the basic observables of these theories, namely expectation values of Wilson lines. Now, I've told you that Wilson lines were characterized by sort of the topology of their links, or various other such things, spatial information, but also characterized by the representations in which these Wilson lines propagate. The rule for the topology for this level rank duality is simple. The topology, a Wilson line like this maps on the other side to a Wilson line like this. Nothing interesting happens in space. In representation space, on the other hand, the rule for the map of one side to the other is more interesting. Wilson lines in a representation on the first side map to Wilson lines in another representation on the second side. And the rule for getting the representation of the first guy, the second guy from the representation of the first guy is well understood. Roughly speaking, in the case of these UN theories, representations are labeled by Young tableau. And what you need to do to get the Young tableau of the dual representation is to transpose the Young tableaus, interchange rows and columns. Okay? So for instance, if you have a representation with only one row on one side, let's say M boxes in the first row, it maps to a representation with M boxes in the first column on the other side. Now, boxes in a row are symmetrized, whereas boxes in a column are anti-symmetrized. Okay? So this is a duality in which, roughly speaking, Symmetrization on one side maps to anti-symmetrization on the other. And that's going to play a very important role in what I'm going to say later on. Okay, so all this so far was review of 30-year-old material. Now, Chern-Simon's theories 30 years ago were studied and so well understood precisely because they were these extremely simple topological field theories that could be exactly understood. Consider now you take one of these Chern-Simon's theories and couple it to massive matter in some representation. Now, the beautiful topological invariance of the Chern-Simon's theory is no longer true. You've got a genuine quantum field theory with genuine local degrees of freedom, but one that flows at low energies once you've integrated out the massive matter to a topological field theory. So if you take Chern-Simon's theories and couple them to massive matter, you've got an example of a non-trivially gapped theory, the kind I was talking about at the beginning of my talk, namely a quantum field theory with genuine interacting degrees of freedom that flows at low energies, not to an empty theory, but to topological field theory. Okay? So in the rest of this talk, I will be talking about these kind of theories. Chern-Simon's theory is coupled to, minimally coupled to massive matter fields in some representation of the gauge group. In particular, I will largely focus on two particular examples. The UN Chern-Simon's theory minimally coupled to fundamental fermions, or the UN Chern-Simon's theory minimally coupled to fundamental bosons. My fermions are just ordinary fermions. My bosons are Wilson-Fisher bosons. Okay, critical bosons. Okay. As I mentioned before, both theories in the previous transparency are genuine quantum field theories with local degrees of freedom that reduce to pure Chern-Simon's theories and so to topological field theories at low energies. Now, with an appropriate choice of parameters, the theories above can be chosen. I give you the parameter map in the next slide. So that once you integrate out the matter on the two sides, the two Chern-Simon's theories, the pure Chern-Simon's theories that you get on the two sides are level rank dual to each other. So actually are secretly the same theory. Okay, so it's easy to do that. One of the real surprises in the study of these theories, study allowed largely by the fact that these theories, even with matter, turn out to be exactly solvable in the large n limit. Okay, one of the real surprises of the studies of these theories is that this low energy duality that has been known for 30 years actually gets promoted to a full duality of the full quantum field theories. So you take these fermions coupled to Chern-Simon's theory, you take the bosons coupled to Chern-Simon's theory, you arrange the levels and the ranks so that after you integrate out the bosons and the fermions, the two pure Chern-Simon's theories become level rank dual to each other. And it turns out that IR duality is actually, the tip of the iceberg. The theories themselves, all the way to the UV, are completely dual to each other. Okay? This is one of the first surprises in the study of these theories, and implies many other surprises, which we will investigate through this talk. Okay, the map of parameters that you have to work with, the map of parameters for n here and k here, nf and kf, nb and kb, and also of masses between these two theories, for which ensures this duality is listed here, but I'm moving on. Okay, the evidence for the duality described above is very extensive and detailed, especially in the large n limit. The key point here is that both sides of the duality continue to be exactly solvable, as I've mentioned, at large n. So we can separately compute various things. For instance, we can separately compute a thermal partition function on one side, a thermal partition and the function on the other side, and just check that under this map of parameters, the two answers, which are very complicated, turn out to be the same. Okay, so the evidence for this duality, the duality has not been proved like no non-trivial quantum field theory duality in higher than 2 dimensions has been proved, but it's certainly true. Okay, now, the existence of this duality throws up various questions, and I'm going to sort of analyze them one by one. Firstly, you can take this theory, and let's take the bosons here. Let's take the bosons here to have positive mass. Okay. When the bosons here have positive mass, the vacuum of the theory is roughly just a set of spins in a parametric magnetic phase, and then these spins are gauged. Okay. So the elementary excitations of this theory are created by the basic spins, the basic bosons. On the other hand, if this mass here goes negative, then what happens is that the potential for the bosons is sort of like a Mexican hat. The bosons want to condense, and then our spins go into what you might think of as a ferromagnetic phase. Except that these spins are coupled to gauge field. So you should think of this as Higgs phase. And then the elementary excitations of this bosonic theory are W bosons. Okay? So depending on the sign of the mass, the basic excitations of the bosons are either the elementary boson spin 0 or the W bosons, which are spin 1. In contrast, for the fermions, the elementary excitations for both signs of mass are just elementary fermions. Okay, so now we reach our first puzzle. How can it be the two theories are the same if on one side the excitations are spin 0 bosons and spin 1 bosons, the other side they spin half fermions? How can it be that these two theories are the same? Sounds like it's just wrong. Okay. So in order to address this question, I'm going to sort of remind you of a certain bunch of elementary things about spin. Okay. Recall that if you have a massive particle in d dimensions, all massive particles in d dimensions appear in a little group of SOD minus 1. Okay? Now, when d is greater than or equal to 3, SOD minus 1 is a non-abelian group because d minus 1 is, but d is greater than or equal to 4, SOD minus 1 is greater than, d minus 1 is greater than or equal to 3, and SOD d minus 1 is a non-abelian group. All representations of this non-abelian group are labeled by discrete integers. Okay? So, and these representations are of two sorts, those that are spinorial and those that are non-spinorial. Spinorial representations are fermions, non-spinorial representations are bosons. And since these representations are discrete, you cannot continuously go from one to the other. On the other hand, in 3 dimensions, the little group is SO2, and the covering group of SO2 is U1. U1 admits, is R. R admits representations with any charge. Okay? So it's conceivable, at least from this point of view, that the spins of a particle can continuously change from half to 1 or half to 0. At least group theory doesn't forbid this. Now, okay. Now this is important because our duality here is conjectured to work in d equals 3, where this little group was SO2, its covering group was R. Now, we've discussed that the duality can only be correct if the spins of the elementary excitations on the two sides are the same. They don't look like the same. They look like they spin 0 for the bosons and spin half for the fermions. But if you do a more careful analysis, you find the following. The naive spin of the boson is 0, but there's a contribution to the spin from the Chern-Simons gauge field. This is something you can compute semi-classically using Noether procedure. And it was sort of implicit in all the early work in Chern-Simons theory. And the contribution to the spin from the Chern-Simons gauge field is simply the dimension of the Wess-Zumino-Witten operator that's dual to the particular representation, C2R divided by 2 kappa. When you add in the contribution of the spin from the Chern-Simons gauge field to the intrinsic spin of the particle, total it up to get a total spin. And you compute the total spin on the bosonic side and the total spin on the fermionic side. Put in all the parameters I've talked about. The two spins match on the nose. This is only possible because the spins were not half or 1. They could just go anywhere, any real number. All of these spins are generic values of k, any real number, but they're equal. Okay, so the first lesson is that in these theories, spins for these excitations don't have to be half integers, they could be anything. Okay, a second thing that might worry you is that I've told you that theory of bosons is a theory of fermions. But the first thing we learn when we study bosons and fermions is that bosons obey Bose statistics, fermions obey Fermi statistics. How can it be that multi-particle states on one side match to multi-particle states on the other side, when one side you have obey Bose statistics and the other side obey Fermi statistics? It just sounds wrong. The way this works is sort of very interesting. It can be uncovered. You see, this puzzle exists even in the non-relativistic limit. In the non-relativistic limit, both these theories are described by Schrodinger equation. Okay? In work that will hopefully appear soon, we've described the Schrodinger equation in great detail. Turns out that the Schrodinger wave functions take the following form. Schrodinger wave functions are wave functions are function of positions times group invariant index structures made out of the indices of all the particles that are participating. Okay? Now, you can work out the Schrodinger equation both for the first side, so bosons in one theory, and fermions on the other side, and on the other side, fermions in the other theory. You can also demonstrate the following. You can also demonstrate that the Schrodinger equation, the first Schrodinger equation that you write down, after a field redefinition, a variable change, maps to the second Schrodinger equation. Okay? But the variable change is an important one. Okay? And the variable change, roughly speaking, converts this invariant index structure I to a dual invariant index structure. And the nature of this variable change is that an invariant that is symmetric on one side is converted into an invariant that is antisymmetric on the other side. Very much like how it worked for Wilson lines. Okay? Now we're in business. Because you see, let's say that we've got a symmetric index structure here, and psi was a bosonic wave function. Then this psi I had to be invariant under symmetric interchange of particles. On the other hand, the variable change converts into a psi tilde, where this I is antisymmetric under the interchange of color indices. Psi I then has to continue to be symmetric under interchange of spatial variables in order that the full wave function be antisymmetric as is required for fermions. Okay? So the lesson of this story goes as follows. It's these hidden gauge variables that in the end contract to singlets. The symmetry properties of those compensate for the difference between symmetry of bosons and fermions, allowing the physical part of the wave function, namely the dependence on positions, to have the same symmetry properties on both sides, even though on one side you have bosons and the other side you have fermions. Okay, fine. Next question. When bosons are weakly coupled, they obey Bose-Einstein statistics. Okay, the number of bosons in a particular energy state is given by this formula. On the other hand, when fermions are weakly coupled, bosons are here and fermions are here. Fermions are weakly coupled, they obey Fermi-Dirac statistics. Number of particles in any given state is like this. Though the puzzle isn't as sharp, one might wonder, how can it be then that if you take these theories at finite temperature, you will get the same answer, even though on one side you might think you should have Bose-Einstein statistics. The other side you should have Fermi-Dirac statistics. Answer to this question is very interesting. When you study these theories in detail, just like for the spins, turns out that there is a one-parameter generalization of both Fermi-Dirac statistics and Bose-Einstein statistics. For instance, the occupation number, we understand these statistics in full detail. Here I'm just presenting the answer to the occupation numbers. The occupation number for for fermions is given by this generalization of the Fermi-Dirac answer. It's a more complicated answer. Okay, it depends on the coupling constant of these fermions. Similarly, the occupation number for bosons is given by this generalization of the Bose-Einstein formula. Okay? Both sides have a one-parameter generalization, a Q deformation, that comes out of the physics of these theories. Okay, now, the occupation number, now you might ask, do these occupation numbers match to each other? The occupation numbers don't quite match, but they do once you multiply by the number of colors. Okay. Once again, this is physically what you should expect, because you've got a single particle state. It could be occupied by one color a certain number of times, but all the colors are equal. So once again, you see that this is what you should have wanted, that the total occupation number, once you sum over all colors, matches on the two sides. Once again, statistics is consistent with Bose-Fermi duality because of the existence of these sort of hidden gauge quantum numbers, without which nothing would have worked. Okay, fine. If you look, it's well known that for ordinary Fermi-Dirac statistics, the occupation number formula at zero temperature becomes very simple. All energies below the Fermi sea are occupied. All states with energies below the Fermi sea are occupied. All states with energies above the Fermi sea are unoccupied. Okay? When you look at this modified Fermi-Dirac statistics, you take the zero temperature limit, this thing doesn't change. in the zero temperature limit, the modified Fermi-Dirac statistics reduces to the ordinary Fermi-Dirac statistics. What about for bosons? For bosons, on the other hand, we find something interesting. Recall that for ordinary free bosons, if you have a chemical potential that is larger than the mass, then there's a catastrophe in this bosonic system. Because states which have energies below the chemical potential, which is possible when the chemical potential is above the mass, are occupied an infinite number of times because the Boltzmann suppression factor e to the power minus beta e turns into a Boltzmann enhancement factor when you include e to the power minus beta e plus mu q. Okay, so for ordinary bosons which are free, you cannot turn on a chemical potential larger than the mass. It's just a disaster. Okay? In these theories, on the other hand, you look at the formula for the modified Bose-Einstein statistics, and you find something very interesting. You find when you take the zero temperature limit, this occupation statistics continues to be well defined, even when mu is larger than the mass. And what you find is that every state below the chemical potential is occupied a certain number of times. Well, this n bar is 1 minus mod lambda b by lambda b. So very much like fermions, except that states are not occupied once. They're occupied on the average a certain number of times. Now, this n bar, when you work it out in terms of the integers, turns out to be kb by nb. So multiplying by nb, you see that the total occupation number, once we sum over all colors, is bounded from above by the level of the Bose theory. So this ultraviolet catastrophe for bosons is regulated by adding this Chern-Simons term, turning bosons into things that look more like fermions. And that's why these theories can be dual to each other. Okay. I'm running out of time, so I skip this technical comment. Maybe half a minute. The technical comment was that, you take a free gauge theory, a very weakly coupled gauge theory, put it on a sphere, you've got lots of matter particles. The partition function obeys a restriction. You only count those states that are gauge singlets because of the Gauss law constraint. In these theories, we've understood how that statement is modified. It's a very interesting and mathematically beautiful modification. You only count those states that are invariants under the Wessamino-Witten fusion rules, where the Wessamino-Witten theory is the Wessamino-Witten theory associated with the Chern-Simons theory. But that's a technical comment, so let's move on. Last point, and I'm stopping, I'm sorry for, yeah. Fine. Lastly, these theories have a mass gap. Right? So they have stable particles that can scatter. Okay. Now, in trivially gapped theories, scattering of stable particles obeys a certain structural constraint. Scattering matrices obey the rules of crossing symmetry. What this means is that if you know the S matrix, let's say for particle going to particle, you interchange an initial particle with a final antiparticle and do something on the other side. That new S matrix does not require new computation. You can get it from analytic continuation from the old S matrix. Crossing symmetry is a proven property for trivially gapped theories for 2 to 2 and 2 to 3 scattering. Okay. Now, the statement of crossing symmetry itself becomes a little complicated, even in trivially gapped theories, when the theories have enjoy invariance under global symmetry. This is because scattering can occur in many non-abelian global symmetry. So because scattering can occur in many different color channels, or symmetry channels. So let me give you an example. Suppose you're scattering two fundamentals to two fundamentals. The two fundamentals can fuse into the symmetric or the anti-symmetric representation of UN. On the other hand, if you're scattering a fundamental with an anti-fundamental, these can fuse into either the adjoint or the singlet. Okay? And when you work out the classical, the ordinary rules of crossing symmetry, you find that crossing in the identity channel, singlet channel, for fundamental anti-fundamental scattering is related to crossing for fundamental scattering in the singlet channel and fundamental scattering in the anti-fundamental and in the anti-symmetric channel by this formula. Similarly, crossing in the fundamental anti-fundamental channel crossing of fundamental anti-fundamental scattering in the adjoint channel is related to fundamental scattering in the singlet and in the symmetric and anti-symmetric by this formula. Okay, this is just classical crossing symmetry. Somebody in the 1960s who cared to do it would have written down this formula. What happens in these theories? In these theories, something very interesting happens. These rules for crossing symmetry, which the textbooks I studied when I was learning quantum field theory told me were sacrosanct, are not true in these theories anymore. It's not that these rules are destroyed, they get modified. The modification is a very beautiful one. You get this formula where every number that you had in the game is replaced by this Q number, where the Q number is defined in this way, where Q is e to the power 2 pi I by kappa. In the limit k goes to infinity, the Chern-Simons gauge field decouples from stuff. So Chern-Simons theory reduces to a theory with global symmetry. In that limit, Q numbers go to ordinary numbers, and you recover the ordinary rules of crossing symmetry. So crossing symmetry is deformed in these theories by Q deformation, at least for this matter content in these theories. Clearly, it's going to be deformed in general. I'm not sure the general rules are known yet. Okay, so that's it. I'm sorry I've gone over time. Let me end with a summary. Non-trivially gapped quantum field theories are qualitatively different from their trivially gapped cousins in many interesting respects. This is a fact that condensed matter physicists have hammered home to us over the last 15 or 20 years. But condensed matter physicists largely study the extreme low energy. When we look at the full quantum field theory, which reduces at low energies to topological quantum field theory, and study the dynamics of the matter fields, we find that the fact that the topological field theory at the low energies is different endows different properties to these matter fields. They have different statistics. They can have non-integer spins. They scatter differently. And the low temperature physics can be very different from what you might expect. For instance, the bosonic catastrophe at chemical potential above mass is cured, behaving more like a Fermi, say. Okay, since non-trivially gapped, the study of the structural properties of these theories is just beginning, lots remains to be understood. I think it's a very cool thing because it's very clearly defined, very clean, and yet you encounter surprising physics. Since non-trivially gapped theories are common in condensed matter physics, for instance in the quantum Hall effect, it does not seem unreasonable to me to hope that some of these novel structural properties that we're discovering with pen and paper now will one day be verified in laboratories. Okay, thank you.
Thank you very much, Professor Shiraz. So we have a small memento for you.